So this question is typically referred to as a power factor correction type question. And here we want to analyze the circuit shown, which describes the 1 kilowatt load before the capacitor is added. And so then before the capacitor is added, the load runs at a power factor of 0.65 lagging. And so the basic idea is that S before the capacitor is added, we call S1. It is equal to the power of the lighting load there divided by its power factor of 0.65. We have 1000 watts divided by 0.65, and S1 then has a value of 1538.5, and the unit is volt amps. In addition, we'll calculate Q before the capacitor is added, and Q then, QL, the inductive reactive power, will be equal to the square root of S1 squared subtract P squared. And that gives us a calculation of 1538.5 volt amps squared subtract 1000 watts squared. And so we'll calculate then QL, the inductive reactive power, approximately 1169. The unit is vars or volt amps reactive. Now, next then we have to think about adding the capacitor. Remember that the capacitor here will be placed in parallel with the load that's shown, C. And the reason why we do that is, well, let's think about if the capacitor were placed here. What that would do is the voltage across the capacitor would subtract from the load voltage such that the load would no longer have its required voltage of 208. And so therefore we cannot put the capacitor in series with the load. The capacitor goes in parallel with the load such that the voltage across the capacitor equal to the 208 volts across the load. And so if the capacitor is placed in parallel with the load, then we should be able to say that after the capacitor is added, we basically now have the circuit shown. And so that means that the capacitor again is in parallel with the load. Now the capacitor here will typically produce some of the reactive power that is required by the load, and we'll see that the load operates at a different power factor from the source, because the source will see a power factor of 0.91 lag, and the load, the lighting load, will still have a power factor of 0.65. And what happens now is that we will see the capacitor here produce some of the reactive power required by the load, such that the source only needs to provide a portion of the reactive power required by the load. And so if we think about now, after the capacitor, we will have S2. And S2 will be equal to the power of the lighting load divided by what we might refer to as the new or overall power factor. And so we have the 1000 watts divided by 0.91, which is the new power factor. And so we would like to then produce a circuit whose apparent power has been reduced to 1099 volt amps from the 1538.5 volt amps we calculated above without the capacitor. And so that would then result in an overall reactive power of Q net. And remember that Q net is equal to the difference between inductive and capacitive reactive power, or in this case QL subtract QC. And so Q net, if it's the total, it will be based on P and this new power factor, or S2 at 1099 volt amps. And so therefore Q net will be equal to the square root of S2 squared subtract P squared. And that calculation now gives us 1099 volt amps squared subtract 1000 watts squared. And we see that Q net much less than the requirement of the load, 455.6 vars, as opposed to the load which requires 1169. And so what that means is that the capacitor will have to produce the rest. Now, from this equation, we will say that QC is equal to QL subtract Q net. And therefore, remember QL above was 1169. Q net, we're going to say is 455.6, which means that QC has a value of 713.4 vars. Okay, now remember that QC is the reactive power of the capacitor here, and we have not calculated the current here. This is a parallel circuit, so the current into the load and the current into the capacitor will be different. It will not be equal to the circuit current over here. So then what we do know about the capacitor is that it is in parallel with the load and the source, which means that the voltage across the capacitor is known. It is the 208 volts from the source. And so what that means is that we have QC at 713.4 vars. We also know that VC is 208 volts. And how we relate these two quantities is with the equation QC is equal to VC squared divided by XC, which is a version of P equals V squared over R, or you know, what we're saying basically is that the power is equal to the voltage squared divided by the impedance, the inductance, the resistance, whichever is appropriately put down there. And so using this equation, we rearrange to say that the capacitive reactance is equal to VC squared, which we know, divided by QC, which we have calculated. And that gives us 208 volts squared divided by 713.4 vars, which was calculated. If we do the calculation, it turns out that XC will be equal to 60.65 ohms. Now that is the capacitive reactance. We have been asked to find the size of the capacitor, which typically means in farads. And so from that, remember that if XC is equal to 1 over 2 pi F times C, then C is equal to 1 over 2 pi F times XC. And so therefore we can write that the capacitance is equal to 1 divided by 2 times pi times the frequency, which has been given as 60 hertz, multiplied by the value 60.65 ohms that we had calculated. And so if you multiply together 2 times pi times 60 hertz times 60.65 ohms and take the reciprocal, we should come up with 43.7 times 10 to the negative 6 farads, and therefore C is equal to 43.7 microfarads, where we have inserted the micro for 10 to the negative 6.